Thank you very much. Thank you for inviting me, and I'm going to talk about the system that we've built now at Coinbase for custody and more exchange. In fact, this is the system that's going to be protecting the vast majority of all the assets at Coinbase. It's joint work with the cryptography team at Coinbase, including Arash Afshar, Yisho Chen, and Samuel Renalucci. Samuel and Arash are here as well, so you can speak to them afterwards. The description I'm going to provide is not a full exact specification of what we're doing, and it won't include all details, and a legal caveat that this is a living, breathing system and it will change over time. But this is the design and architecture of what we are using, and it will give a very clear and transparent understanding of how we're protecting assets at Coinbase. So I want to start with very briefly talking about a couple of the general challenges of asset protection with current systems. We can divide them possibly into offline, online, and some types of hybrid. But an offline system is an air-gapped system. The keys are on a machine which is not connected to the internet in any way. And this can be built with very high security. But it's important to understand that offline systems are not necessarily secure. Just to be, to say the obvious, if you take a laptop that you buy at, I don't know, at Best Buy, and you put it in the cupboard in your office with a lock that can be broken in 2 seconds, and you connect with a USB drive to upload the transactions and sign, and then download the signatures, this is going to be extremely poor security. So questions like, how indeed does this offline system actually communicate with the world? How do you upload what you want to sign on and download the transactions? How do you physically protect that offline environment? Who has access to the machine? Can a single person go in? Is there physical security around it? All of these questions are very, very critical when it comes to building offline systems. And offline systems generally result in challenges regarding time to sign. And there's also a very clear trade-off between the more controls we have around it, then this, of course, will increase time to sign. And that can be a problem with SLA because what's crucial is to protect the keys, but also to enable people to do business. If people can't transact quickly, then this is going to be a very big problem. In an online system, at least a naive online system, keys are held in some server, and there are obviously very, very clear security challenges. These are highly lucrative targets, things like supply chain attacks, insider access, 0 days. All of these are huge threats. And therefore, such a naive online system will typically not be suitable for large amounts. But the way that a lot of these systems are set up is that you'll have some amount in an online system which will give you day-to-day liquidity. You'll have a large amount of reserves in an offline system, and you'll transfer back and forth as needed. Okay, and obviously in an online system like this, you get immediate response time. One thing that we always keep in mind is this idea of a single point of failure or a single point of attack. And no matter how much you protect a system, when it's so lucrative, and I'm talking about billions and tens of billions and even hundreds of billions of dollars worth of value, then these are very, very attractive targets, and we have to think about how much we can protect them. So again, offline systems can be made secure, but they also to some extent become a single point of failure because at the end you have a key sitting on a single machine in a single room with maybe not a single person, but with some people, some small number of people in that room with them. And although there are very, very good mitigations, these mitigations are costly also in terms of time, and the threat is always still going to be there. I do want to stress that there's a very big difference, however, between an offline system that you use for ongoing signing on a regular basis and an offline system that you'll use for more infrequent operations, for example, like key generation ceremonies. The reason is that people can be more careful, and more care can be taken when something is infrequent rather than when something is very, very frequent. Okay, so when you do something only every now and then, you're generally more nervous about it, you're more careful about it. This is the reason why social engineering works well on things that people do all the time. Okay, let's talk now about a system that we've built. It's called CryptoCurrencies Vault. It's already being used, and it will be used for more and more products in Coinbase for custody, for exchange, and so on and so forth. A couple of design principles that we had are, one, flexibility. We need to be able to support multiple products from the system. We don't want to have many, many systems. And therefore, this system, CryptoCurrencies Vault, has to be able to provide different security trade-offs and response speed, usability, and so on and so forth, so that it can meet the needs of each different product. In terms of security, we want no single environment with key access. We want strong separation. We want different types of entities with strong separation between them. And we want defense in depth throughout. So we use MPC, or threshold signing, to obtain this strong separation and flexibility. We can have different numbers of entities of different types, and we can tailor that to the product. The asset keys are shared amongst the entities, and they're never brought together throughout the entire life cycle. And backup is also an extremely important part of the system, because I always like to say that there's only one thing worse than having your money lost. It's money stolen. It's when you lose your money yourself. So backup needs to be done very, very carefully, both in terms of disaster recovery, in terms of being highly protected, and we use public verifiability to make sure that we're able to, in an offline way, in an ongoing in an ongoing manner, to verify that the backups are safe. Okay, so we have three entity types in CryptoCurrencies Vault. We have an offline environment, we have human approvers, and we have MPC servers. I'm going to go through each of the different entity types, and then I'm going to talk about how we actually carry out the operations. So the offline environment is what you would expect, some type of offline machine, and a separate store of key shares. Exactly how that is built and what is done, these are things that we are not going to talk about. But I will say that it's a physically secure location with strict access limitations. So a lot of control around this environment. Importantly, unlike classical offline environments, in CryptoCurrencies Vault, the offline environment only holds one share of the key. So it's not a single point of failure. Having said that, and this comes back to the defense in depth that I talked about, the security of this offline environment is designed in a way that even if it would be the same even if we had the full key there. So we're not taking any taking any discounts on how much to secure that environment. The second are human approvers. These are people with devices. So these are human operators, and they may have a mobile, they may have a laptop, and they hold shares of a threshold decryption key. Okay, they're the secret shares that they hold. So think, for example, TDH2 by Shoup and Gennaro. And this threshold key is generated via MPC out Vault generation amongst the human approvers. And how does this connect to the asset keys? There is one share of the asset key which is held by the human approvers, and this share is encrypted under that threshold encryption key. Okay, so we have one share being held by the offline environment, one share being held by the human approvers, but that share is encrypted under a threshold encryption key, so you need a quorum of approvers in order to be able to access that share. And the human approvers can be arranged in any access structure that you would like. We can define a quorum, and our system supports quite advanced access structures, so you can think of actually defining a tree. And within that tree, you can have AND nodes, OR nodes, and threshold nodes, and you can do anything you want. So you can say 3 out of 5 and 2 out of 4, and of course, you can do much, much more complex access structures as well. And an important property of this human improver environment is that they are humans, meaning that they're sometimes available and sometimes they're not. And they're also, if they're using their laptop, they may at some point just close the laptop because they're finished working for the day, or they finished their shift, or whatever it is. And therefore, we do not require the human approvers to be online at the same time. We do not require them to be carrying out ongoing operations with each other. And therefore, the type of operations they can do must be of that type only. Importantly, I'll just note that the threshold decryption indeed requires each party just to generate a single partial decryption. they do not need to interact with each other in order to finish this process. And the third entity type is the simplest type, I guess. These are just simply MPC servers or online MPC servers. Each server holds their own database of key shares. They're always online and they can interact with each other. So how many shares do we have? We have one share for the offline environment, one share for the human approvers, and one share for each MPC server. So if there are 4 MPC servers, you would have 6 shares overall. Okay, the infrastructure for each of these environments is very, very different in terms of the type of machines they're running on, their location, who has access, and by definition, that gives us very strong separation. And strong separation is crucial for any MPC or threshold signing system, because if you, for example, split a key between 3 machines, and all those 3 machines have the same administrator sitting in the same room running the same operating system, yeah, maybe it's better than a single machine, but it's not a lot better than a single machine. It's actually quite close. Whereas if I have them in very separated and different environments, that protects me against 0 days against the systems. It protects me against corruption of a certain subset of the infrastructure of the organization, and so on and so forth. The offline environment, without their participation, there simply is not enough key material online, and therefore nothing can be signed. The human approvers are somewhere in between an offline and an online type entity, because those devices can be disconnected by the humans, and at which point, once again, if there isn't a quorum of humans who have approved, there will not be enough online key material to sign online. And the MPC servers are also very highly protected. They can be locked down in the server infrastructure, and depending on how one wants to deploy such a system, they can be also administered by different sets of administrators. They could even be in completely different environments, like different clouds and so on and so forth. Core KMS Vault can be instantiated in multiple ways with different types of entities. You don't necessarily have to have all 3 types of entities in every instantiation. And furthermore, you can have a different number of each entity within your instantiation. You may have different numbers of MPC servers or different numbers of human approvers, depending on the type of product that you're building and what you're trying to protect. And you can also have these entities in different places. For example, for a non-custodial product, you could have human approvers at the customer and MPC servers at Coinbase. For a custodial product, you would have MPC servers and human approvers all inside Coinbase. So this is the way it could look. You have an offline machine. Here, for example, you have 4 MPC servers, and maybe you have 5 out of 20 human approvers, and therefore you would need all of these entities in order to carry out any operation. Okay, we're now ready to talk about how operations are carried out. We'll start with key generation and backup. If it's a system with an offline environment, then the property that we want is that the key is never online until it is used, and therefore there is a key generation ceremony in a special offline environment. And I say a special offline environment because this comes back to what I talked about initially, that security in an offline environment can be much higher when you're doing infrequent operations, like a key generation ceremony. And in this ceremony, generate a bunch of keys. The keys are then shared and encrypted under each recipient's key. So the offline environment has 1 key share. The human approver share will be encrypted under their threshold encryption key. And each MPC server has its own public key, and each of their shares will be encrypted under their own public key. And then that will be exported from that offline environment. If there is no offline environment in the system, because that's the type of a vault we're using, then it will be an MPC key generation operation. And at key generation, as I mentioned beforehand, all key shares are backed up using publicly verifiable backup with a quorum of backup entities, and that quorum, again, is a different set of parties that is defined. Their backup shares are protected using hardware and software. So, for example, you could have UBHSMs or things like that to protect those shares. The fact that it's publicly verifiable backup means that given the asset public key, given the public keys of the quorum backup entities, you're able to efficiently verify that the ciphertext indeed holds the correct asset key and nothing was corrupted. You don't need to expose any key material in order to carry out that verification. That's a very, very important property. Okay, now we'll get to the complicated process, which is how do you sign with this system? So the first step is at the offline environment. The offline environment receives a transaction request, loads the key share in however that offline environment operates, and that key share is then sub-shared into shares, one sub-share for the human approvers and an additional sub-share for each MPC server. So in the diagram we had with 4 MPC servers, you would be sub-sharing this into 5 sub-shares, 5 additive shares. This just means random values under the constraint that they sum to the offline environment's share. And these are then encrypted under each recipient's key, again, the public key for each MPC online server, and the threshold encryption key for the human approvers. And this sub-sharing is fresh and different in each transaction. That means that as long as one of the entities later is honest and they erase their sub-share, the other sub-shares will be just complete garbage and meaningless, and we don't care if they remain in the system because they don't, information theoretically, even hold enough information to be able to do anything. So this is the way it looks. You can see that step number 1, you have a transaction request over here. Then the offline machine will sub-share and generate the sub-share to each of the parties, encrypt them and output them to the system. And of course, you have this some operator in the offline system which is going to load the appropriate share for the asset key. Step number 2, these shares, encrypted sub-shares, have been output from the offline environment, and the human approvers are next in line. Each human approver up to the last in a quorum. So if we have 5 out of 20, then the first 4 human approvers to connect will work in this way. The last one worked differently, so I'm separating it into 2 steps. So each human approver will receive the transaction request and will verify transaction attestations. This is extremely important because it's security of a signing service is, of course, only as secure as the keys themselves from being stolen, but it's also only as secure as the machine who can issue a request to sign. I don't need to steal your key if I can ask to transfer all of the money protected by that key to my address. And therefore, attestations are important. These are signed attestations from different systems inside Coinbase. For example, there's a system which does fraud mitigation, looks at the parameters of the transaction, and if it's a suspect transaction, will not issue an attestation. You would have an attestation also from the service that receives the request externally. You would be verifying at the very least both of those attestations, and the system can support multiple different attestations, again coming back to preventing any single point of failure. So it's not just who holds the key, it's also who can tell me to actually sign on this transaction. And these attestations are verified by every single entity in the machine, in the system, with the exception of possibly the offline system, because we want that offline environment to be very, very simple. But again, that's a choice of whether we want or not, but all the others always will verify before doing anything. Now, each human approver, after verifying the attestation and saying, yes, these are fine, will generate a partial decryption of the shares that are needed. There is the approver share, and there's also the sub-share generated by the offline environment. So there are 2 shares here that partial decryptions need to be generated for, and this is what that human approver will do. And then those partial decryptions will be re-encrypted under the public keys of the approvers. The reason why this is done is because once you have enough partial decryptions, it then becomes a public operation to decrypt. So to prevent anybody else from decrypting, these partial decryptions are re-encrypted under the regular public keys of all of the human approvers. That's everyone up to the last approver. The last approver who joins or who accepts the transaction will do the same thing initially. We'll verify the attestation, we'll obtain the partial decryptions of the other parties, we'll decrypt them, and then we'll just be able to combine the partial decryption, if its own partial decryption with the others, in order to get the shares themselves, the approver share and the offline sub-share, and we'll add them together. Okay, so that's what you can see here. We now have each human approver over here. Each human approver, they provided their partial decryption, and the last approver now has its own sub-share, its own share, the approver share, and also the sub-share from the offline environment. We're now ready to start signing. So each MPC server also receives the sub-share from the offline environment and also loads its own share from its database, its protected database. Again, after verifying all attestations, all the MPC servers do this as well. And once we do this, the MPC servers and the last approver all agree on who is playing. Because there are a number of approvers, and maybe there'll be more than one approver who claims to be the last approver, we want to make sure that everybody agrees, that we have consensus on who is participating, because this is what MPC protocols or threshold signing protocols assume. And we also make sure that the secret material they have correctly adds up to the private key. We do that, again, in a secure process in order to make sure that nothing bad happens, for example, if the offline environment is corrupted and actually sent bad subshares. Okay? We have a zero, we're always assuming that anything in the system can be corrupted, so everything is validated from the beginning to the end. Once that is done, the MPC servers and the last approver can sign. Here, the last approver needs to remain online, but remember we talked about the asynchronicity. That's between different human approvers. The fact that the last approver will remain online, that is fine. They're interacting with online servers, which are always online. So they run, sign on the message. They then they refresh the sharing of the asset key. So the asset key changes every time, except for the offline environment. No one talks to them. So the refreshing is done of the shares of the MPC servers and the human approver, but not of the offline environment. Then all state information is erased, and we finish the signing process. So it's a rather complex process with multiple steps. But once it gets started, once the offline environment has output its shares, it will complete very, very quickly. The speed with which the offline environment will respond will depend on how it is actually constructed, and that's beyond the scope of this presentation. Okay, so that's what I think I need to go through the diagrams, but you can see the processes that I talked about. The last operation I want to talk about is approver administration. We need to be able to add approvers, remove approvers, potentially change the quorum structure for whatever reason. We want to refresh the approver threshold and decryption key so that it's not always the same. You can't slowly go and steal a share one at a time from each party. And all of these are also run via MPC. Of course, also generating the share, which I talked about, generating the threshold decryption key is also done in MPC. So we have MPC protocols for doing all of these different operations, and that's crucial because we need to manage those keys and the users. And important things you might be thinking: why are we using a threshold decryption key? Why not just have each approver have their own public key? The reason is if an approver leaves and we have a new one coming, we need to issue them a new private key, a new public key, then now the encryption of all the asset keys is no longer valid. And we're not going to start re-encrypting 1 million, for example, asset keys every time someone leaves or joins, both because it would be computationally expensive, but also because it would itself be a security risk because you bring online keys that are not in use, and that's something that we don't want to do. Also, all of these operations require assigned admin quorum approval. So how do you add an approver? You need to have, there is a set of administrators who need to approve that. You get a signature, and only then are you willing to go ahead and carry out the operation. A couple of properties. In terms of security, a key cannot be brought to signing without the approval from the offline environment, a full quorum of approvers, and all MPC servers. This is crucial because of the attestations. The attestations are verified by each and every entity, and that ensures that key misuse is very much mitigated. When you're using an offline environment, before a key is used, it is never connected in any way, shape, or form. And there is no single point of failure attack in the system. Everything has multiple points that you would need to attack simultaneously, both in terms of holding the key, providing the attestations, and so on and so forth. And there is strong separation also between the types of systems. The types of machines that the human approvers hold are very, very different from the types of machines that the servers hold. And there's a very different type of machine also for the offline environment, which is an extremely secure machine that it cannot be used for anything at all. How do we achieve flexibility and speed in this? We can deploy the system in multiple configurations. And this is also important for MiCA compliance because we can put some of these entities in different countries and therefore ensure that without that country's approval, you won't be able to carry out an operation. So here are some configurations. You can have all of the entities, which is what I showed until now. You have an offline environment, human approvers, and MPC servers. But the number of human approvers and the number of MPC servers, the access structure, the location of those human approvers can all be very different depending on what you need. Do I need a custodial solution where everyone is in the US? Do I want someone in the UK from MiCA? Do I want human approvers at the customer for a non-custodial? All of those can be carried out within the same system. A second type of system is one without an offline environment, so you have MPC servers and human approvers only. It's the same flow exactly as beforehand, but you don't start with the offline environment sub-sharing. So the system works in the same way, but you suddenly now get very different properties. It's faster than above, but it still has the human approvers who can disconnect their machines to prevent the material being online. And you can have a system which is fully online or MPC servers only with very fast response time. This will still be much, much more secure than classic online systems because there's no single key sitting on any machine. Attestations are verified by all of the machines, and you can have strong separation between the MPC servers as well, but you'll get essentially the same response time in practice as a single server. Defense in depth, I mentioned. All devices and servers are heavily locked down. The approver shares are encrypted both with a secure enclave of the user device and also external UBHSMs. There's a zero trust approach to all devices in the system. We don't trust to any machine. Everything is verified. Nothing is assumed to be okay, and that's a crucial design decision. There are many controls around the offline environment, who the approver operators are, how they can work, what machines they use, and much, much more. All of that is crucial to the security of the system, and I like to say that I think we have quite a good cryptography team at Coinbase, but we have an incredible security team at Coinbase with huge operational security experience, and of course their contribution to the system is very, very crucial as well. Thank you very much.
Thank you, Yehuda. Time for questions.
Very interesting talk. So I want to understand the human approver part better. Maybe I missed. Is it defined what's the last approver? If not, then how the MPC server know which is the last approver in a consistent manner?
So you can define who you want the last approver to be, particularly if there are not numerous approver sets in the access structure. You can define that you want the last approver to come from a specific set. But even if that set has more than one approver in it, that's why we have the step of consensus amongst the MPC servers and the last approver to agree on who that's going to be. So if two approvers come and say, I'm the last approver, work with me, you only get one consensus because the MPC servers need to agree with each other and with that last approver.
Go for it.
Thanks for the talk, and apologies if I missed this. I was wondering which threshold signing protocol you're using and what the challenges were in terms of gathering things from the literature versus inventing new ideas in-house and things like that.
Yeah. So it really depends on different protocols of course, for different settings, if it's two-party or multi-party, but here it's almost all multi-party. So for Schnorr or EDDSA, it's my protocol. For ECDSA multi-party, we're currently using a protocol by myself, Ariel Noff, Iftach Heitner, and Samir Anlucci. But we're looking at moving to the latest protocol by Abi Shalat et al., which is 3 rounds. The challenge is, in general, for all deployment, we're very, very strict about verification. So we will verify ourselves. We will have an independent review within our team, another independent review within the security team at Coinbase, who works with the internal and external consultants, and external review as well beyond that. So everything that we take is very heavily reviewed. The fact that something has been published is not something that we say, okay, then it's secure.
Just a quick follow-up, is the first one with Nofranucci and Heitner, is that public or
Yeah,
not
it is
yet?
public, of course. Yes, everything's published.
Thank you for the talk. Very interesting. Quick question from my end is about the complexity of all of this. So that scares me, just how many moving parts there are and how many different sub-protocols and so on and so forth. And then implementing all of that correctly. What measures have you taken to ensure that it's implemented correctly and to, in general, reduce the risk stemming from that complexity?
Okay, so we have, in terms of the engineering team, we have a team that has been implementing and working with MPC and threshold cryptography for about a decade. Significant number of members of the team have been working on encryption and cryptography products for 20 to 30 years. So a lot of experience in that sense. The way that we work is that there's a theoretical protocol, theoretical paper. We write, our team, the cryptography research team writes a clear specification, and from that specification an implementation is carried out. We verify that independently verify in our team that the specification matches the theoretical protocol and that the code matches the specification. BlockSec, which is part of the security team inside Coinbase, also verifies that the specification matches the theoretical. First, they verify the theoretical paper is correct. They verify that the specification matches the theoretical protocol, and also an independent team in Coinbase as well verifies that the code matches the specification. And then we go to external, an additional external audit beyond that to do that whole process again. So we're very, very rigorous. We're very, very careful. Is any code perfect? No, that's why there's defense in depth. I'm extremely happy to have security at my back to make sure that we're not relying on anything whatsoever, but we have, I think, the most rigorous process that I've seen in industry for implementing all of this.
Thank you. And are you able to share like rough TCP sizes or things like that? Like what's the lines of code on this kind of thing?
I don't know. Do you know?
Okay.
I don't know. That I don't know. Sorry.